So good afternoon. Welcome to UQRUG, the gathering for users of our users of all skills. My name's Nick. I'm one of the technology trainers here at UQ Library. And today we also have with us Raimundo, who will be giving an overview of machine learning and tidy models in R. There we go. Raimundo's turned on his webcam there. Now, as always, before we do jump into things with the overview today, we'll be going through the ways of working for today, just the basic overviews of how we work here at UQRUG. So you can see on the main screen here that I've shared, we've got the UQRUG website. So this is a Quarto-based code written website where you can find all of our resources. You can find all of the past events and upcoming events. You can see the past meeting notes from previous sessions and a link to some other community groups that do similar things to us. If you do go to this website, which I will pop that in the chat. There you go. If you go to that website, you can check this out. After that, if you click on this little link here with a little document, that will take you to the Hedge doc that we'll be using today, where you can put in all your questions and anything like that. And I'll put a link to that in the chat as well, so you don't have to necessarily navigate that. Go to there and it'll come through to our little overview. So basically this is a little document that if you go to the link, you can edit. And the reason I want you to edit this document is so that you can add your name to the list of people who are here today and also any questions that you do have. All right, so while everyone goes and fills out their name in the attendees list, I'll just go through the other bits of working here. So as you know, we meet the last Wednesday of every month, so that's today from 12 till 2 p.m. We're both here in person at the Central Library and also online. If you can't make it, you can also go to the UQ chat and chat with us there. And you can also email the training team for help. So as I said, we start today by adding your names to this page, and then I'll get you to add your questions to this page. And once everyone's done that, we will go to our intro to machine learning with Raimundo. That out of the way, I'm going to pass over to Raimundo, who's going to give us our overview. And again, it's really cool to see Raimundo has made his presentation using Quarto. So we've got another one that we will be putting up on the website again.
All right. Thank you very much, Nick. And thank all of you for being here. I am Raimundo Sanchez. I am from Chile, and I have been here at the UQ for the last 6 months. So I'm working here as a research fellow in the School of Health and Rehabilitation Sciences, and I love coding in R. I've been programming in R for the last, I don't know, maybe 12 years. I started during my PhD, and I never stopped. And I often get the question, why don't you use Python instead of R? And the answer is because I have always managed to solve my problems with R. I have never needed the Python capabilities. So I believe that R is a strong language, and most of my work is done in this framework. So today I will be talking to you about machine learning. I have worked a lot in machine learning. I taught machine learning courses back in Chile. So I will try to give you a brief overview of all the main concepts regarding supervised machine learning specifically. And we'll give you some tools for implementing these models in R. I prepared my teaching notes, and I will be sharing that with you in a R Markdown documents that I will be sharing right now through the chat, and it's the same link that you can see below my slides. All right, it's exactly the same content, but it's more detailed, and all the code is commented also. So let's start with a brief introduction to machine learning. Machine learning is a framework, is a discipline that tries to uncover the patterns within a set of data, a set of inputs and outputs of within our data, between all the characteristics. So if we simplify this to the lowest level, we can just understand machine learning as a function. We try to model a variable, an outcome variable y as a function of input variables x, a vector of variables, because we can manage a lot of dimensions, a lot of multivariable problems. So this is like the most simple way to look at machine learning. Of course, there's a lot of other stuff that we can worry about, but on a broad sense, this is kind of what we are trying to do. We're trying to find the best fit, the best form of that function f that can capture the patterns present in our features, our input features. Many times when we talk about machine learning, this is conceived as a black box. So I love the black box because it allows us to simplify the whole process. So we have some input data, we have this AI, this machine learning model, this black box that processes this data inputs and transforms it into an output. That's essentially what we're trying to do. There's a lot of ways that we can do this, like I'm sure you have heard about neural networks or support vector machines or Bayesian models. Those are just names of the types of black boxes that we can use to model the relationship between the output data and the input data. So in this workshop, we won't dive deep into the mathematics of each kind of model. We will only overview them and see how can we implement these kinds of tools in R using the tidyverse package. Many of these models can get too complex too fast. So this model complexity is a key question that we have to address during machine learning. Here in the graph, we can see what happens when our models get too complex. So if we have two curves, the above curve is the curve of the data we don't know, and the below curve is the data that we do know. So if we train a too complex model with too many parameters, then our model will be learning the patterns of the data instead of learning how to generalize them. So we will lose our ability to generalize results if we choose an overcomplicated model. So and this is known as overfitting. That's what happens when we have more parameters than we should. And to avoid overfitting, we can recur to the data sampling techniques. The most common technique in machine learning is to take your data set and split it into two sets. One set for training our models, one set for finding our optimal parameters, and then another set for testing them and for measuring the results and the accuracy of our models. So this step is crucial in the assessment, the correct assessment of a machine learning model without incurring in overtraining. There's different ways in which we can split this data. The most common is just made a simple single split, but we can also do some cross-validation. That is when we do this split several times and compare the results of all the different splits. Well, machine learning is a discipline that is live. As we speak, there's a lot of researchers developing new algorithms, new ways to use computing power to model data, right? So there's a lot of types of machine learning. Here we are looking at the essential ones, but there's a lot of other types that we won't mention today. But I just want to define this concept that are the most used ones. So you can essentially divide machine learning into two big groups, two big families. One that we call supervised learning, and the other that we call unsupervised learning. And supervised learning can also be divided into classification and regression, and unsupervised learning mostly relates to clustering tasks. In the case of supervised learning, these are kinds of problems where we know the label, where we know the independent variable that we're trying to predict. So if we have a data set with a lot of features and we have all our independent features like the X vector, and we also know the dependent value, the value that we're trying to predict, then we'll be dealing with a supervised problem. And this supervised problem can be separated between classification and regression. Classification is when we're trying to predict categories, when we're trying to predict discrete values, true or false, or if or maybe some other type of categories. And regression is when we are trying to model the relationship between our independent values and a continuous numeric variable. So that's a big difference. Most algorithms can work for both kinds of supervised problems. The only thing is that we have to specify in the code. But that's the main difference between the two types of supervised methods. On the other hand, unsupervised learning are data set that operates with unlabeled data. That means that we don't know the value of the Y variable. There is no Y variable. So we can't predict anything. The only thing that we do with unsupervised learning is to understand the relationships between variables, the relationship between data points. And so it's a very helpful tool to perform clustering analysis, which is the most common application of unsupervised learning. In today's workshop, I will only be focusing on supervised learning. I will be talking about the implementation of both classification and regression algorithms. Maybe we can do another overview on another time for clustering methods. So we'll be working today with the tidymodels package. I assume that most of you have some knowledge about R, and maybe you have been exposed to the tidyverse package. The tidymodels is kind of an extension of the tidyverse, but it's designed for implementing, building, and evaluating machine learning algorithms. If you load the tidymodels package in R, you will see all these warnings. It's because it's composed by a lot of sub-packages. So tidymodels have packages for measuring machine learning models, for specifying them, for a lot of stuff that we'll be seeing today. From a practical perspective, we'll be trying to deal today with a specific problem, and that means that we'll be working with specific data. So we'll be analyzing a data set that is very common in machine learning uses. That is the New York City flight data set for supervised machine learning. This data set has 300,000 data points with 19 columns, and is comprised by flights that were departing close to New York City in the year 2013. So we have a lot of these variables. And in this case, we will be trying to predict if the flights will be delayed or not. So if you can see here, we have a lot of columns. We have the column of delay that is in minutes, and we will try to predict that value, all right? So for making the things a little bit simpler, we will transform this column. Sorry, I will be back. If you see the values of the delay, there are mostly a continuous variable. We have a lot of different values for delay. We will transform it into categories for simplicity's sake. And we will try to predict if a given flight will be delayed by 15 minutes or more. So we will discretize the variable of arrival delay. So if the delay is over 15, we will define it as late, and it's below 15, we will define it as on time. So we are transforming this numeric variable into a category. And then this step also is selecting some of the variables. We will be modeling the delay in function of different variables, such as departure time, the flight, origin and destination, the air time, the distance of the flight, carrier, date, and the time of day of this flight. In this step, we are also removing all the values with missing values. We are also mutating all the character values as factors, as categorical variables. And the last step, I just take a sample of 10,000 rows because the dataset is so big that your computers will probably struggle with all the datasets. So that's it. So let's go down to the tidymodels components. Tidymodels is comprised by a lot of different parts. Thanks. And the main part, the most important part, is the engine, is the type of model that we will be working with, the model specification. Tidymodels offers a diverse selection of machine learning algorithms, and many of these algorithms require some definitions, some parameter definition, some mode definitions, and engine definitions. The mode definition refers to the classification or regression. Engine definition refers to different packages of where these machine learning algorithms are implemented in R, and parameters depends on each model. And this is important because the tidymodels package is just a wrapper of other different machine learning packages in R. There's a huge collection of machine learning packages. Each package has its own ways to input the data, define the formula, output the data. So it's tricky to work with all of them. And the best thing about the tidymodels, it just uniforms the way in which we analyze all these models. So it's a very convenient wrapper that allows us to use all the other libraries, machine learning libraries that are already developed in R. And that's it. So the model specification, then, again, refers to the type of models, and we will be reviewing the most common models that we see in supervised learning. Of course, this is not an exhaustive review. There's a lot of models that I won't be reviewing today, but still for your first glance at this, it will be enough, I think. So, for example, if we want to model the input data with the output data as a decision tree, which is a very popular and old type of model in machine learning, we just use the tidymodel function called decision tree. So in this function, we have to specify some parameters such as the tree depth, that's the amount of branches the tree will have, and the minimum amount of points that will be allocated in the last one of these branches. There's a lot of theoretical implication in this kind of parameters that I won't be defining today. So we want to study in deeper detail. You can ask me for some additional resources. So we define the model as a decision tree with these parameters, and we also define the mode. In this case, we're doing classification, and we are also defining the engine. In this case, the engine will be R part, which is a common library in R for dealing with decision trees. Decision trees are popular algorithms because it has high interpretability. It's not such a black box. It's kind of a white box. And it's easy to handle nonlinear data, so it's a pretty popular model. But it can have some bias. So of course, in all the models has their pros and cons. And my suggestion always is to test all the different models and see which performs the best. The second algorithm that I will be showing is the logistic regression. That's also a pretty old technique. Back in the day, this kind of algorithm wasn't defined as a machine learning algorithm. There was just like a statistical tool. Machine learning is a new concept. But looking at it as a model that allows to relate input and output variables with a function, this makes sense to define it within the machine learning framework. It's like the simplest of the models in machine learning, but still is still used a lot in many applications. So it also has high interpretability, is very efficient computationally, and has strong resistance to overtraining. And main cost, the main cons is the linearity assumption. And so when we're dealing with nonlinear data, it can be a problem. So in this case, it's the same thing. We have a logistic reg function as defined by the tidymodels package. And then we create the object logistic regression, and then we add the mode of classification and the engine of the generalized linear models, which is the base R package for dealing with logistic regressions. There's a lot of engines, different engines for each one of these algorithms. So if you simply ask for help in the R console for the logistic reg function, for example, you will see all the packages that can be tuned, can be used to tune the model, such as GLM. There's a lot of other packages that can also do the same thing. The third one is a model called the naive Bayes. This model applies the Bayes theorem to calculate the probability of a class given a set of features. And it's called naive because it assumes the independence between all features, which is a naive assumption. It's an assumption that not always stands. But still is a very popular model that is used a lot and still works pretty well despite this naive assumption. So in the case of the tidymodels, we have this function called naive Bayes that we are also setting with mode classification and with an engine called CLAR. You can see that in the case of the naive Bayes function and the logistic regression functions, these functions does not need parameters. We can define some define some parameters that they are not necessary to train the model. So I just leave it blank and it works pretty well. So the process of this model it trains pretty fast. It's super efficient computationally, especially on high dimensional data. High dimensional data is data which has a lot of columns, a lot of features. So that can be a problem for some algorithms. But naive Bayes works pretty well with this type of datasets. And the cons, I already mentioned this, the naive assumption that can limit its performance. Then we have another model, the multi-layer perceptron. Multi-layer perceptron is like the formal name for neural networks. Neural networks sound a lot cooler, but multi-layer perceptron is like the formal definition. And it's a model that consists of multiple layers interconnected, of interconnected functions that process our data. So in this case, multi-layer perceptron is the function MLP. This function only allows for shallow neural networks. I'm sure you already have heard about deep learning or deep neural networks. For implementing that kinds of model, we will need another framework. tidymodels is not set up for that. You will need probably TensorFlow or something like that. So in this case, we were talking about shallow neural networks with only 3 layers and 1 hidden layer. So here in the parameter, we are defining the amount of neurons in the hidden layer. And I define it as an arbitrary number. Now it's 10. You can tune that parameter later. And also we're setting the mode as classification and the engine as NNet, which is a common library in R for dealing with neural networks. But as well as the other models, this model also can be performed with another engine. The process of this model is to model, it allows model nonlinear relationship in data. And the main cons is pretty susceptible to overfitting because it has a lot of parameters. So like we were saying a couple of slides before, the bigger the complexity, the more susceptible is our model to overfitting. And it also has a low interpretability. So I think that this is like the main example of the black box that you see in literature. Everybody refers to this kind of model as a black box because it's impossible to understand the sensibility the models has to any of the input variables. For example, the logistic regression, we can measure the sensibility of the model. We can measure the elasticity of the model the model's performance according to each one of the input variables. But with this kind of model, it's a little bit trickier. So that's why it's called a black box. There's also a kind of models called ensemble models. Random forest is an example of these ensemble models. And what ensemble means is that they take a lot of simpler models and combine them. So random forest, what does is like take, I don't know, a huge amount of trees. In this case, for example, we're defining the amount of trees as 15. So this model, what this model will do is to train 15 separate decision trees and then merge them all together. But this model doesn't merge the trees, it merges the results. So it takes all the results and takes a centrality measure like the mean or the median and generates like stable prediction based on that. That makes this model also a black box, because since we are merging the results of different models that are built differently, we won't know the feature importance and in the classification task. So this model has high accuracy, high resistance to overtraining, and handle high dimensional data, but it has low interpretability and can be computationally expensive because we are dealing with a lot of models. It's like a meta model, right? So it can be expensive, but it isn't always like that. Another model is the k-nearest neighbor. This is one of the simplest ones. This model determines a class of a data point by considering the neighbors in the feature space. So this model just measures the Euclidean distance between one point and the other. And based on what their neighbors are classified, it just averages the classes and takes the majority votes. The function for this kind of model in tidymodels is nearest neighbor. We can define the number of neighbors here in the parameters, and also we're defining the mode of classification and the engine as KKNN, which is also another library or package for machine learning in R. One of the pros is easy to explain and capture complex relationships, but can be computationally expensive and doesn't handle high dimensional data really well. And the last model specification that I'll be showing today is support vector machines. These machines try to identify a decision boundary known as an hyperplane to separate data into different classes. And most of the time it generates additional features in order to generate the separation. So these additional features can be set here in the degree parameter inside the SVM poly function. Here we are dealing with a function that's called support vector machine underscore poly, because it's a support vector machine, a polynomial support vector machine. There's other forms of these models, but I won't be describing them today. But if you want to know more details, you just can ask me later. These models can handle high dimensional data pretty well, and it's pretty robust and against overtraining, but it has the cons of being computationally demanding because of the construction of support vector machines. These machines try to solve a highly dimensional optimization problem. And it tries to optimize the Lagrangian function of, it's super complicated. I won't be explaining it, but it's a optimization problem with a lot of restrictions, so it can be super expensive computationally. So that's the model specification, and it's the main course, it's the main part of the tidymodels approach. But there's a lot of other important parts that we should also address. For example, we should also address the data sampling step. Tidymodels package has a lot of techniques and a lot of functions for sampling data. For example, we can see a function called initial split, where we pass in the data and the proportions, and this function will separate the data into training set and testing set. with this proportion, like 75% of the data will be allocated to training and the rest 25 for testing. And we can also set a cross-validation. Here's the function for bfold cross-validation. Bfold means that we are separating the data between training and test 5 times, 5 different times. So we will have 5 different sets, and these 5 different sets will be used to train the model, and therefore we will have 5 different results, and we can compare these results and compare the variability of these results.
Sorry for
yes.
interrupting. Would this one allow also for keeping some, or this technique can be used for also keeping some of the data, like a subset of the original data for then testing the model?
Yeah, that's a good question. You can do this cross-validation set with the original data, or you can also do it with the trained data. So you have the train, you subdivide the trained data into this new test and new train, but retaining the original test data for the model performance assessment.
Okay.
So that can be done. The only thing that you have to change is the data parameter that you will input to the default cross-validation function. So in this case, we're passing the trained data. You could also pass the flight data, which contains the whole data set.
Okay.
So that's the only difference.
Okay.
That's regarding data sampling. And then the recipes. I think that this is one of the most important parts of the tidymodels framework. And the recipe, what does is it explicitly defines the relationship between the variable y and the variables x. So this is the step where we tell the model what are we trying to do. So I have 2 examples here. I have first a simple recipe, a simple example, where what we're doing is we're creating a recipe, and this recipe will be that we're trying to model the delay in function of departure time, distance, and time hour, which are our numerical variables. This is something I forgot to mention. Machine learning only works with numerical values. It doesn't work with categorical variables or character variables. So if we have that kind of variable, we have to encode it into numerical values. So in this case, we're trying to model the delay in function of the arrival delay in function of departure time, distance, and time hour with the trained data. And that's the recipe specification. But of course, the tidymodels approach has also a lot of functions that allow us to do some more sophisticated recipes, such as the one we're seeing below. So in this case, we are also trying to model the arrival delay in function of a dot. That dot stands for all the variables, all the possible variables. So it's everything in the data set with the trained data. So until this parenthesis is the same as here, but we are also applying the pipe operator to add different steps within this recipe. For example, in this line, I'm telling the model that the variables flight and time hour are ID variables, are just variables that I will use to identify that observation, and therefore the model will ignore these variables, will not consider them for the recipe. Then I'm also adding a step date, where I'm transforming the day and extracting from the date the day of week and the month of each flight. I'm also adding a step holiday, where I take the dates and I contrast them with the holidays of the US. So this generates a column, a feature, true or false, if that date was a holiday or not. Then I'm adding a step to dummify all nominal predictors. This is an encoding step. And what this means is that we're taking the categorical variables and transforming them into columns, into numerical columns. So if we have, for example, I don't know, 10 airports, we hope, because we have the the destination of the flights, the 10 airports then will be transformed into 10 columns, one for each airport, with a 1 or 0 if that airport was the destination for each flight. So it's in this step where we are transforming non-numerical variables into numerical variables. And finally, the last step, we are removing all the predictors with 0 variance. Zero variance means that the values for all the data points are the same for a given column. That's a column with zero variance or zero standard deviation. All the values are the same. And when all the values are the same, then that feature doesn't add any value to the predictive power of the model. So we will just ignore it.
And I'm sorry for interrupting.
Sure.
So if you have true or false data, you also have to encode it to 1, 0?
That's a good question. True or false data, in R, are interpreted as a logical data.
Yeah.
And logical is like a subclass of numerical data.
So it's okay.
R knows how to deal with binary features. Yeah. So you don't have to transform it. But yes, a good question. So this step is pretty important. There's a lot of other steps, functions that aren't using today, but you can also dig into the recipe documentation so you can learn how to use it. Then after the recipes are done, we can merge our recipe with our model specification into a single structure. These structures are called the workflows. So what we're doing right here is that we are creating a workflow for New York City flights. It's a workflow, it's a void, an empty workflow. And we add to this workflow a recipe, any recipe. And we also add a model. In this case, I'm adding the tree model, the decision tree. You can add any of the 7 specifications that we look at or any of the other specifications that we are revising today. So this is where we build where we define or create the workflow object in R, but it's in this line of code where we fit the model. This is the line of code where our machine learns. This is the line of code where our machines are fed with the data and calibrate its parameters, and all the magic is done. So this can be computationally expensive. So I warn you, if you're trying to run the code in your computer, this can take a while. Maybe not this one, but certainly the cross-validation takes a little bit longer because it has to train the models 5 times in this case. So there are different ways to fit a single model and a cross-validation workflow. These are the 2 specifications, and obviously will give different results. Once we train the model and the model is calibrated, we have the parameters, and therefore we can make predictions with it. We can assess these predictions using the metrics that are provided within the tidymodels framework. There's a lot of different models there's a lot of different ways that we can assess the model's performance, different metrics, KPIs. In this case, for example, I'm showing the RUG curve, which measures the ability of the model to predict. And we can see that this model doesn't have very good prediction power. This curve should be in this way, should be attached to the borders of this square. So there's simply a fast and an easy way to assess this kind of models, and it's the same for the cross-validation. We just run this line of code, and we can have different kinds of metrics. In this case, we're having the accuracy and the area under the RUG curve. We can see that we have the mean for each one of these values. We can see the amounts of cross-validations that were run and the standard deviation of each one of these metrics. So there's a lot of different metrics in machine learning. I won't be discussing them today, but of course, if you have more interest in learning about them, you can just ask me and I can help you with that. And finally, the last step that it's also pretty useful in machine learning applications has to do with hyperparameter tuning. When we define, for example, in our decision tree, the depths or the amounts of leaves within each branch, the amount of nodes, we define like a fixed parameter, but we can test different values for each one of these parameters. So that's what we call hyperparameters specification. In this case, I'm just showing a simple example that we create an object of a decision tree but instead of defining a fixed value for each one of the parameters of the model, I just define this tune, which is a placeholder function, and then with the tree grid, we can test all the possible combination of value between these two hyperparameters to tell me which one of these combinations has the best accuracy, the least error, and therefore we can set correctly with an objective way the hyperparameters of each models that without this analysis will be an arbitrary decision. So that was my last slide. So thank you very much for listening, for your interest. And now we are opening to questions.
Excellent. Thank you for that.
How was the time?
Yeah, it was well timed and everything. That was wonderful. Thank you so much. I feel like that was a lot of stuff that you covered there.
Sorry, I tried to do it.
And I think you did a good job given the complexity of all that. Like there was a lot of things, and I think it makes sense in my brain. So thank you for that. That was
Cool.
great.
Thank you very much.
I definitely have some questions, and I know there's questions in the chat, so I'll throw to everybody else first, and then I'll ask my questions. So if anyone does any questions, please put them in the chat. I can see that Car has questions. But do either of you two have questions as well? So Car had some questions as you were going. So if his first question was, would you consider principal component methods to be unsupervised learning? Because it's that kind of clustering.
Yeah, there's a lot of places where they put the reduction and dimensionality reduction analysis within the unsupervised learning. It makes sense to me. I chose not to include them today because I wanted to keep it more simple, the explanation. But yes, not only principal component, but all dimensionality reduction techniques are, of course, unsupervised learning, because those are models that actually learn the patterns within the data, and they just map these patterns into new features. That's the output. Instead of clusters, we have new features, a new feature space. So it makes sense to call them unsupervised. Yeah, but there's a lot of more algorithms than principal component analysis. Maybe we can do another overview on those.
Yeah, I'm almost considering having PCA as its own sort of overview 1 month. So that's
cool.
That's a whole other rabbit hole to go down.
Yeah, right.
And the other question was, is this V-fold cross-validation the K-fold cross-validation? And I don't know what that question means.
It's exactly the same. Maybe there are two schools of thought, one that uses the V or the K, but it's exactly the same. So don't overthink it.
Cool. All right.
The V and the K stand for just the number of times in which you do the validation.
Exactly.
Using different letters for the repetition. Okay.
It's just a variable name.
Okay. This might be a dumb question, but would it be able to do mixed models? Like look at mixed models, or is it like?
What are you calling mixed models?
So I don't really know too much about it yet. I'm just sort of learning about it. So in animal breeding, we do linear mixed models to look at mixed models machine.
Yeah, this framework allows for simple models. So mixed models, I think, is a little bit more complex than what we're looking at here. Mixed models are like a special case of regression analysis, and in this case, we're dealing with like the simplest regressions. But you can set up your data from mixed models to test it with machine learning algorithms. But this library, these packages, does not have implemented the tools for solving mixed models type of problem or another type of complex regression.
But it might have like a singular model, like use machine learning algorithm.
Yeah, in fact, a linear regression analysis can also be considered machine learning. It's the simplest form of machine learning. So any model that has parameters that are calibrated through a process of reducing the error can be considered a machine learning approach. So in that case, mixed models can be considered as machine learning. But also will depend on who you ask.
And like you said it well, it is a combination of random and fixed effects.
Yeah, right.
Cool. Keep throwing things in the chat if people have questions, but what I was going to ask is like, when do you think someone should consider using a machine learning approach with their data set? Is it like, if you're going to try and predict anything, then you should be leaning heavier into this sort of package, or?
That's a great question. I think that the main use for this kind of models is when you don't know or you don't have an explicit hypothesis on how the variables relate between each other. So the alternative to machine learning is explicit modeling, where you tell the model what is happening, because you have a lot of literature, a lot of experience in your field that tells you how the variables, how the system should be behaving. So you can model explicitly the system, and that's what most scientists do nowadays for the last 30 years. Yeah, exactly. And you can see some people are switching to machine learning because it has this powerful framework and has a lot of predictive power, but not always that predictive power not always allows you to answer all the questions. So it depends on a lot of factors. But I think, for example, if you want only prediction without explanation, machine learning sounds like a pretty good approach. But if you want to explain also, you want to understand and dive deep into the model's performance, maybe machine learning is not the best tool for doing so.
Yeah, that makes sense. It's sort of like, it feels like there's a bit of a gradient within machine learning as well as to how like how much you want to be able to explain. Like the linear side of things seem like, yeah, you can explain what happens after that, whereas some of those are very much, as Catherine's pointing out.
Yeah, the thing is that machine learning algorithms are like universal generalizers. So they can generalize anything, including the functions that you are modeling explicitly in your field. So that's why they can achieve similar results in terms of accuracy. But if you have an hypothesis on how the system works, you can also model it explicitly. And when you model it explicitly, you also are applying some computational algorithms. When you model a system explicitly, most of the time you have to optimize the parameters of that system as well, and you apply some kind of optimization method, right? And parameter tuning is not exactly the same, but it's a closely related field.
Yeah. Thank you. I feel like that was a really good overview of all of the different things that you can do. Where would you suggest someone go to get started from here? Like, is there a good tutorial you can suggest, or just is someone using this a good approach? And like, what would you suggest for someone using with their own data as well? Like, you can learn to do something, but it won't necessarily plug into your data.
Yeah, I think that the most difficult part in a practical sense is to generate a tidy enough data set for this to work. That's the most difficult part, because once you have the tidy data set, you can just copy and paste all the code that I just shared with you and change the variable names, and this will work. But the tricky part is to build that data set with features, with all numerical features and with enough observations. So I think that most of you will struggle with that before struggling with the model specification or the stuff I was talking about today. So my biggest suggestion will be to go out and try stuff and get your hands dirty. And that's the only way to learn these kinds of stuff. So I think that this overview is a good starting point, but you can also, there's a lot of other resources. if you dig into the tidymodels documentation, it's amazingly detailed. So I think that would be like the natural step after digesting this workshop.
Cool. So we'll put a link to this workshop on the, I mean, we'll put the workshop that Raimundo has created here onto the UQRUG website, as well as the link that Raimundo shared to his GitHub before. And so you can go through and run and copy that code and run it in R.
Yeah, I can show you right here.
Yes.
And do those different things.
Yes, I was gonna ask that. I'm like, please show us anything in R.
Right now I am presenting this presentation is online. So this is the resource I shared with you. I also have the slides. But if I remove this, you can see a full markdown document with all the stuff that I was talking about today. So the types of machine learning, supervised, all the stuff. And here's all the code also, and the code is commented. So you can just copy paste this in your own RStudio and just run one line at a time. Here's all the detail. It's a little bit further explained that what I managed to explain today, but I think that this will be pretty helpful for all of you.
Cool. So there's a whole tutorial there. And if people want to learn how to make a tutorial that looks like that, I'll be releasing the video from the session we did on that a few months back soon as well.
Perfect. Sounds all right.
And then, so then what you do is that, let's say you can go to New York City and they can give you a set of their, like these are the flights that we have scheduled for today. What are the, how do you use then what is generated after all this machine learning thing?
Sorry, here, I forgot to mention that. That's actually a great question. Here in this line of code, we are looking at a function within the tidymodels approach that is called augment. And that function, what does is it takes our data and it generates predictions for our test data. So if you have new observations, you have new data that you want to predict if the flight will be arriving late or it won't, you will have to apply that function in order to generate all the possible predictions. And this will predict the class, delay or not delay, and will also will provide probabilities of each one of those classes.
For each flight.
For each flight, exactly.
Cool.
Yeah. Well, that's the magic function that I forgot.
Like we worked really hard creating this group model.
What now?
That was going to be my last question. Like, what's the output look like? Like, what do we do with it now that we have this model?
Yeah. Cool.
There were a couple other questions. One is, how do I choose my number of neighbors in KNN?
That's a hard question to answer. Common practice tells us that we should aim for a number of neighbors below 10. But the hyperparameter tuning section that I show at last would be the appropriate way to measure this. So in this section, the hyperparameter, we can tune the number of neighbors. So we can test the same model with the same input, the same recipe, with 1 neighbor, 2 neighbors, 10 neighbors, with all the possibilities, and like a brute force approach. And then we keep the one that generates the least error or the best accuracy. That would be the way. Like all things, yeah.
Yeah, there's not just press button and it does thing. Another question that came through directly to me, it seems. Is there any good R machine learning book that you would recommend? I mean, there's a lot of cookbooks out there. Is there one for machine learning in R that you'd recommend?
I don't have a book in top of my mind, but I can check into them and make a recommendation. When I learned this stuff, there wasn't a single book. But I will check into it. Yeah, I don't have an answer.
Yeah, fair enough. I mean, there's so many things in the tidyverse have, you know, Hadley Wickham's made some book on it or something, so there's likely something there. There's one of the Catherine's pointed out that the tidymodels website have a tutorial on their page. Of course they do, looking at sea urchin data. Brilliant.
Nice. That's cool. Another data set that people can use to run this one and play before going to torture their own data.
I'm pretty sure they used to have like the non-tidy models, like just do a linear regression, things like that as well on that website.
Thank you very much.
Thank you so much.
Sorry, we're having sound issues in here, Catherine, so I'm the only one who can hear you.
Oh, okay.
Yeah,
I'll put it in the chat.
cool.
Catherine was just saying they have non-tidy models in the web as well.
That's right.
Have a quick look at that website that Catherine shared. So this is the tidymodels website. I'll just turn my dark mode off. Yeah, so once you've had a look at Raimundo's stuff, you can have a look at the tidymodels one if you're also wanting to get into doing some machine learning. Cool. Yeah. All right. Well, if people do have extra questions, you can go ahead and add them to the page. It looks like no one's got needs any assistance this month, which is why we do these overviews, so that we can still meet together and get something out of it. I can see that Catherine, nope, we just got some people saying some other things. I can see that people don't have any other questions, but I do want to talk about a couple of UQRUG things before we wrap up, because I've got some ideas for the next couple months as we get towards the end of the year. Oh, we've got Catherine said, I'm pretty sure because I used the ANOVA linear regression as a resource for the UQ library. Right, so they used to show that on the tidymodels thing, but they don't anymore. Some non-tidy examples. Okay. Cool. Well, I think that'll wrap up the first half. Thank you again, Raimundo. That was excellent.
Thank you very much.
I didn't know where to start to play, but I mean, it's pretty obvious. You go to the tidymodels website, there's a tutorial there and just do it. But now I have the encouragement to do so. So I don't think I have a data set that I need to create a model for, but I can go and play. So I think I will do that now. So thank you. As always, I'll put a copy of the recording. As always, I mean, it's a new thing. I'll be putting the copy of this recording onto the YouTube page for UQRUG. I'll send that out hopefully next week. I'll also try and get the copy of the slides from today also onto the page. But leading up to next month, what I wanted to discuss was how we're going to do UQRUG for the end of the year. It always gets a bit tricky because we aim for the last Wednesday of the month, but obviously the last Wednesday of the month in December is going to be, what's that, 2 days after Christmas. So we won't be having a UQRUG 2 days after Christmas because, I don't know, I'm sure most people won't be here. I won't. And then that makes interesting questions for November. But end of November is also ResBaz Queensland. So it's the Research Bazaar in Queensland. ResBaz is a kind of like a little conference sort of thing for researchers to share their data and techniques, and there's a whole bunch of different workshops going on. Wow, that is not looking great on my screen. There you go. I think I was really zoomed in from something before. So yeah, it's going to be here at UQ at the Mickey Building on the 21st, 22nd, and 23rd of November. What's that? Yes. Yeah, so it's a good little conference that you can present a few things at, that you can come to and present at if you want to, but it's mostly for people to come along and upskill in a variety of digital tools. So there'll be a whole bunch of Python classes, a whole bunch of R classes, and just general digital research techniques and things like that. So everyone's welcome to attend. Registration will be opening soon, and so I'll let everyone know about that. But the reason I'm bringing this up is because, well, not just because I'm on the organizing committee, but also because I'm thinking of having UQRUG during ResBaz, so doing like a special UQRUG. It will mean that we are not running running UQRUG on the very last Wednesday of November. It'll be the second last Wednesday of November. Hopefully, as everyone's okay with that slight date change. But also, the other thing that I was thinking of doing is for next month's overview, doing a bit something more of a silly overview. I've discussed it with a few people in terms of that sort of thing. So just instead of using purely for research processes or potentially intimidating processes, looking at some of the other fun sides of using R. So I'm going to put something together where I haven't exactly formulated what it is in my mind, but just doing something silly with a package. There's all sorts of different packages out there that do strange things. And, you know, for example, I came across one that will play like sounds from a video game once you've finished processing your data, so that when you're waiting on this model to process, it makes, you know, a victory sound from Final Fantasy or something like that, instead of you just being like, oh, it's done. So I'll present something like that with the intention of having a early UQRUG in December. And I think what I want to do to encourage a little bit more participation from everybody is have a bit of a competition where I will give a overview of a silly thing you can use R for in November, and then I want to encourage everybody else to do that for the early December rug. So we'll have a silly rug in November and December, and I'm going to put some sort of prize together for the people's choice in terms of who has the best, most silliest, or, you know, whatever, however we deem it, the best one by audience decision. There'll be some sort of UQRUG related merchandise that I'm going to procure between now and then. So yeah, I just brought that up to just get a kind of feel from everybody in terms of what they think of those different suggestions. Yeah, in the room, what do you think? People online, what do you think? Are you comfortable with not doing it the last Wednesday of the month? And what do you think of having a go at making something silly in R? See, that's good. That's good. We can talk about machine learning one week and then how to make funny sounds come out of R the next week, that next month. That's fine, right? What's that? Yeah, you can absolutely have teams for the competition. Yeah, I don't see why not. Brilliant. All right. Well, there's a bit of interest behind that, so I'll. Oh, can we still have questions on modeling in these rugs? Yeah, so we'll still have the usual drop-in help session in UQRUG. Absolutely, that's the main purposes of RUG, is for people to ask questions. We just have these overviews to keep people interested and keep people coming. Yeah, so cool. Yeah, if people still have questions about modeling or whatever you have, yeah, absolutely bring it along. ResBaz will have a few drop-in help sessions as well, so you're welcome to join those at the same time. But yeah, it will also be at a slightly different time during ResBaz. It's likely going to be later in the afternoon rather than midday, just because there are speakers at ResBaz during the middle of the day. But I'll send out an email with all the details of the time leading up to that. So ResBaz is not free. No. So the fee for ResBaz, I think, will be about $40. But that includes like morning tea and lunch for 3 days, and then as many workshops and things as you want to go to. So like, if you think about it purely from a lunch perspective, you know, it's good value. It's good value. The other side of it is if you are wanting to, if you can't afford the fee or anything like that, or if you do want to volunteer, you can also volunteer to help out. You know, putting up signs and that kind of thing. And then you don't have to pay the fee. Yeah, so a good example of a volunteer is Catherine, who is in the chat at the moment. Catherine's going to be volunteering to help out with a few different things. Just going to name drop you there. Cool. All right. Well, it looks like no one has any further questions in the chat today. And it looks like there's no questions going in the Hedge doc. So we might have an early finish today unless anyone else has anything they want to talk about. No? Cool. Brilliant. Well, again, thank you to what was that? Thank you again to Raimundo for coming in. You're a jack of many trades, so we might have you back again next year to do more things if you're interested. Yes, that's exactly what I was going to say. Is from School of Human Movement. So you've got measuring like things off measuring devices. You've got spatial stuff. You've got machine learning. So there's a number of different areas that I think definitely would be of interest here. I know I convinced Lynn to come along today to potentially ask you questions about that, but that might be one to line up for another chat another time or now. Cool. All right. Well, if there's no further questions or anything like that, I guess we'll wrap up for today. Thanks again, everyone, for coming. I'll send out an email in the next week or so with all of the details from today, and then hopefully one probably the week after that in terms of what's happening in November. Thanks again, everyone. See you next time.